All right, so I'll kick it off here. If you just popped in, welcome back to day 3 of 3. A little bit shorter this morning or this late afternoon or whatever time zone you might be in. We have a good hour of a mix of themes: cryosphere, oceanography, solid earth, and interdisciplinary. Just like the other 2 days, we'll go 4 minutes, just over 4 minutes, and then go into one Q&A session afterwards, but you can use the chat along the way to also interact with authors or with your peers. We're going to start with cryosphere. Evan Wilson will kick us off this morning with a quick lightning talk on improved detection of small-scale mass change signals in Greenland and Antarctica using Grace follow-on laser ranging data. Evan, the floor is yours.
Can everyone hear me and see my screen?
Yes, loud and clear, good to go.
Great, awesome. Hi, everyone. My name is Evan Wilson. I'm a PhD student at the Department of Aerospace Engineering Sciences at the University of Colorado Boulder. And today I'll be talking about the improved detection of small-scale mass change signals in Greenland and Antarctica. So current fully inverted monthly GRACE Level 2 solutions are limited to about 300 kilometer spatial resolution by temporal aliasing, while mass change signals in Greenland and Antarctica can be smaller than the spatial resolution of the current Level 2 products. We can use the line of sight gravity difference approach developed by Gabati Farr et al. In 2018 to examine the sensitivity of both the K-band microwave ranging system and the experimental laser ranging interferometer on GRACE follow-on, because a long orbit analysis allows us to examine the spatial resolution of each sensor without the impact of temporal aliasing. This PSD on the right shows the KBR in blue diverges past 60 CPR, while the red, the LRI, continues to decrease, which is the shape we'd expect to see for real gravity signals. But what we want to do is see spatially how this kind of PSD manifests, especially in the Arctic. So to compare the KBR LRI and LRI with each other, I've used an ISAT2 mass change grid from Smith et al. 2020, which uses ISAT and ISAT2 data for Greenland and Antarctica from the period of 2003 to 2019 to create a mass change trend. And I've generated synthetic LGD from this mass change grid to compare with LRI LGD and KBR LGD. And for this first bandpass I'm showing from 5 to 60 CPR, we can see that all three look largely very similar. And the same thing is mostly true for 60 to 100 CPR. So this is kind of at the edge of what we'd expect the KBR to be able to detect real mass change signals at. But we can see for the KBR that noise is starting to creep in, while the LRI and the ISAT synthetic LGD look very similar. And at 100 to 150 CPR, we can see, again, that the KBR just becomes completely dominated by noise. And notice that I've changed the color bar here. And while the LRI is clearly able to still detect real mass change signals, even at this very high frequency. For Greenland, the same is largely true, although we can see even at low spatial scales in Greenland versus the just 3 months of LGD that I'm using, which is June 2019 to the end of August 2019. The comparison with the trend yields a lot of differences. There's a lot of seasonality in mass changes in Greenland, and just as a limitation of a comparison with the trend, we're not getting the best match. But even with that being said, we still see fairly good agreement. And again, we see that the KBR starts to have noise at a 60 to 100 CPR, and at 100 to 150 CPR, KBR is completely dominated by noise again, while it's clear that the LRI is still able to resolve real mass change signals that are even reflected in this nearly 20-year trend. And because the LGD LRI enables us to use the full sensitivity of the LRI at very high spatial scales or very high spatial resolution, we can also use it as a validation tool. So here I'm comparing a trend made from the standard Goddard mascons and then also the Goddard high resolution mascon trend from Loomis et al. In 2021. And for 5 to 60 CPR, again, we see pretty good agreement across the three. Same thing for 60 to 100 CPR. But for 100 and 150 CPR, we can
1 minute left.
see that the magnitude of the standard mascon trend is much lower than the high resolution mascon trend. And the LRI LGD validates that amplitude, which is very cool to see. And just to put it in perspective, these very high spatial are very high resolution components still are very significant amplitude. And if you just plot the spherical harmonics from 100 to 150 from the high resolution Mascon trend, you get that the equivalent water height is still about 0.2 meters per year, which is very significant. And so some takeaways, using a long orbit analysis, we can clearly see the LRI is able to resolve real mass change signals beyond what the KBR can. And because of that high spatial resolution, due to the long orbit analysis, which minimizes the impact of temporal aliasing, we can use LRI-LGD as a validation tool due to its improved spatial resolution. Thank you. And if you have any questions, please feel free to reach out to me.
Thank you, Evan. We'll keep going with the cryosphere theme. Ingo Saskin from the Alfred Wegener Institute will talk about the Arctic glacier mass variability in GRACE and GRACE follow-on data and its covariation with permafrost under synoptic atmospheric forcing.
Yeah, thank you very much, Felix. So I'm Ingo Saskin from the Alfred Wegener Institute. Felix, you already introduced what my talk is about, so I'll just tell it on to the next slide. So in 2022, we discovered this strong anti-synchronous variation of mass anomalies in northern Arctic Canada and Svalbard. So you can see on the right-hand side, annual mass balances recovered with GRACE. And you can see the striking contrary behavior between the mass balance anomalies. So always when we have a cold year in northern Arctic Canada, we sort of had a warm melt year in Svalbard and the opposite way around. There are just a few exceptions in this observation period. So the idea was, so we traced this back to, a joint atmospheric forcing, but the idea was, can we actually see a similar impact in the other glacier systems as well? So one thing was, of course, can we determine the mass balance of these glacier systems in sufficient accuracy? And what do we do in regions where we don't have glaciers left, such that we get a circumarctic view on this? So we decided to include permafrost data, active layer thickness, and specifically from a remote sensing product, but also from in situ data, to trace this back to a temperature forcing that should then synchronize with the temperature forcing that you would expect for the glacier systems. So this was the idea to fuse these different observations. So we had basically three different observation streams. So GRACE follow-on data, a combined GFZ JPL CSR solution. Then we used the remote sensing product from ESA, representing the active layer thickness, circumarctic, and also an in situ network of active layer thickness measurements. So we applied some criteria on the extent of the time series and how many gaps there are allowed in this time series, and then used a statistical method called factor analysis to try to isolate covariations. So the temporal variations that is inherent in all of these observations. So this is the variable f here, and this is connected to the observation by this factor loading matrix, which sort of describes how much and also with which sign this covariation impacts these observations or represents these observations. So the result is basically something like an Arctic impact index. Here you can see sort of the variation, which has then also, of course, some climatological meaning in the sense that, for example, if this index is high, we have a cold conditions in Siberia and northern Arctic Canada, and as I pointed out before, warm conditions in Svalbard, but also other parts of the Russian European Arctic. So this is the index, and then we try to follow up. This is sort of what we constructed, and then we try to connect this to the atmospheric modes of variability. And this is shown here. You can see then we decompose the geopotential height at 500 hectopascal into during summertime. So these are summer means into the main modes of variability. And we found that we find a significant correlation with these indices and our principal components for the EOF1 and EOF4, which are shown here. So EOF1 is something like a mix of this NAO type pattern plus green blocking type
1
situation.
minute left.
Yeah, but also EOF4 has sort of a higher spatial granularity, so to say, higher modes of variability, and we also found that this is essential to describe also the more extremer variations and represented in these indices. So then we again went back to the observations by regressing the index onto our observations, and this is sort of the results that you can see here. So you basically get a pan-Arctic view on the impacts that are driven by or connected to these atmospheric patterns. And you can see, for example, that you always have a synchronous behavior between permafrost and glacier regions on opposite sides with respect to the North Pole, and then neighboring regions. So it's like a clover leaf. The neighboring regions vary asynchronously. So there's still a lot more to tell you about with regard to the study. If you're interested, just scan the QR code or read the paper or just contact me. Thank you for your attention.
Thank you, Ingo. We'll keep going. Actually, next on the agenda, we would have had Michael Croteau. Unfortunately, being at NASA Goddard, I think he's also not able to join, and I don't see anyone else from the team. Just checking real quick. Is there anyone here that was going to present Mike's and his team's work? I don't think so. That's unfortunate, but they're going to upload their presentation into the online portal, so you can review it there. We'll leapfrog that and then keep going with Isabella on Antarctic ice mass loss since 2002 from satellite time variable gravity missions. Isabella, I don't hear you yet. You might be muted or just not talking.
I'm muted. Thank you. Okay, let me just share my screen.
Yes.
And then I should share maybe. Oh, then let me go back to the start of the presentation and the laser pointer. 1 second. There we go. So I'm going to just talk today.
You need to share,
Hang on a
please.
sec. Yeah, you're sharing the wrong screen, Isabella.
Okay. Okay. Sorry.
No problem.
I failed.
No, you didn't.
Okay. So now I'm still sharing. No.
Yeah.
Okay. Share. Yeah. Microsoft PowerPoint. Share. There we go. Now I'm
Right.
sharing the right one. Correct.
Correct. Yep.
Okay.
Continue to share and then the
yeah.
pencil thing.
Yeah, thank you. Sorry. And I tried, guys. Okay, so I'm going to talk to you a little bit about, walk through the change in mass since 2002 for the Lance of Grace, and about from Greenland and Antarctica, and then to interpret, I'm comparing with SMB. I want to point out, we're going to go in more detail, but a little bit like, so Greenland show in 2012 and 2019, two big increase in mass loss. They are caused by an increase in runoff, followed by some colder summer. And then I'm going to just point out another couple of things. We had a pause in the mass loss in a more recent year, like after 2019. And I'm going to just show you, it's comparable with the one that we observed in the initial period. So we can look at the mass loss also as a map, from Grace. And so if we look at Greenland, we find that, basically all the ice sheet is losing mass at the entire periphery, but the mass loss are larger in the southeast and in the northwest. And overall, the only area now we observe a significant an acceleration is the north, although when we extract the time series, we'll see there's no significant, but we can see an area here in which we had an increase in mass loss, but overall, both the southeast is decelerating and part of the northeast. If you look at Antarctica, the mass loss here is focused on some key region, and we have higher mass loss in the Amundsen, Bailey Anson, and the peninsula, but also lower mass loss in the area of Totem, Moscow, and Wonderford, and which is Scolia Basin CD, and then there's Cook, Nimin, and Metz. And we have mass gain in Queensland Land and Saipol Coast, which is due by slowing down of the closed basin. If you look at the acceleration, we still have acceleration in the area of the Amundsen Sea sector, but and also in the area, but not anymore in the peninsula, and in the area of Cook, we still have some increase. So if we're gonna look at the different region, again, here are like two big melt. We can see that after 2010, there's a change in the regime. We have a series of summer slower, smaller melting in summer after 2012, but even more significant after, the summer of 2020, 21, and 22 are about 2-3 times less than the one of 2012 and 2019. Overall, we have a pause in the surface mass balance in the southwest and in the northeast, but sustained glacier loss in the northwest, southeast, and north. And overall, northwest and southwest dominate the loss. The highest percentage in loss in percentage of SMB change is occurring in the north. If we move to Antarctica, here, SMB dominate the signal in Queensland Land and also in CD, the area of Totem, Moscow, and in the area of Cook, so the basin DE. And ice discharge dominated the Amundsen Sea sector, here the peninsula, and also, overall, the Antarctic overall mass loss. Overall, the mass loss is dominated by what is going on in the Amundsen Sea sector, and we find the Queensland Land in
1 minute left.
in most recent year is increasing by about 22% is surface mass balance, and this is a very consistent behavior we observed earlier. If we compare the first pause with the second pause, they're very comparable, except they are coming from slightly different region. There's more change in East Antarctica in the second period. And just in conclusion, we observe a pause in acceleration for both the mass loss of both the ice sheet. If we look at the entire period, we have a pause in Greenland after 2012, which is associated with a succession of colder summer. Pause in Antarctica in 2019 is due to increase in precipitation and is very similar in amplitude to the one that we observed earlier in the record of Grace. Queensland Land is a sustained precipitation change since 2009 with an increase of about 23% of the mass. And I think that we want to be careful. I mean, I think that what this tells us that we need a longer record. And so when we interpret the 22-year of Grace extrapolated over, for a century trend, we have to be careful because there is a lot, especially in Antarctica, there's a lot of interannual variability. And also there are a lot of changes that are occurring more recent year. And I'm done.
Thank you, Isabella.
And now I'm exiting and stuff.
We have one more talk in the cryosphere theme this morning from Tyler Sutterly and his team. Ice sheet mass balance from satellite altimetry gravimetry fusion.
All right. Good morning. Sound okay?
Sound okay, and your slides are up. Yeah.
Cool. All right. I'm Tyler. I'm presenting this on behalf of my team of Brooke Medley and Matt Siegfried. I am fortunate to be able to look at mass change from a few different angles, largely from Grace Follow-on and ISAT 2. This is a similar plot to what Isabella was showing, but this is averages over 6 years. So from the entire Grace and Grace Follow-on period over the past 6 years, Antarctica has been overall in a state of mass gain, as Isabella alluded to. Basically, we launched 2 great missions, and then Antarctica decides to go a little bit screwy, and we want to know where this variability is coming from. To set the stage, for altimetry, one of the three main ways that we measure ice sheet mass balance, we measure volume. So we measure the surface of the ice sheet, that's measuring volume, and we need to remove what's known as firn air content. Firn, you can think of the top of the ice sheet as like Swiss cheese. The thickness of the Swiss cheese is bigger when you have the presence of holes. Ice sheets are the same. There's a bunch of air at the top. And so if you melt it down and refreeze it, it'd be thinner. So we need to remove that air to get the mass. And typically what we do is we take our observations and remove a firn model to get the mass. But these firn models have a lot of uncertainty, not just between the different realizations of them from like different modeling centers, but also just compared with observations of in situ firn. So we flipped this on its head. We decided to take Grace follow-on and ISAT2 data together and try to solve for firn content. So what we did is we converted our ISAT2 measurements into series of spherical harmonics and then removed Grace from that to get a smoothed version of the firn air content. So we ruined our resolution. And then we decided to use the firn model itself, decompose it into a series of empirical or orthogonal functions, and then nudge the principal components using our observations from Grace and Grace follow-on. So basically we can solve for the atmospheric forcing and Grace, atmospheric forcing in mass change, and we can detect that in Grace and Grace follow-on. And it's really small changes. There's not a huge amount of nudging to go from what the off-the-shelf models get to what we can see with Grace and Grace follow-on. But it makes a big difference in if you're wanting to go from volume into mass. This is sort of what our results look like. This is Greenland and Antarctica. As Isabella alluded to, Antarctica has been gaining mass over the past 6 years. And overall, that's been compensating for the sustained mass loss of West Antarctica. Greenland's still doing its thing. There's been a couple of years of decreased mass loss, so less mass loss, more towards neutral. But the 2019 was still a major year, and 2023 also lost a lot of mass. So this is sort of the picture. But with our technique, one great thing that we can do is we can decompose it into its components. And this is where you can really detect what's happening. So West Antarctica on the bottom, still doing its thing, still losing a lot of mass. It's over the 6 years, it's really comparable to like the first 10 years of the Grace mission. So it's still losing a lot of mass. But the story right now for this current period is that there's a lot of regions of mass gain, and that's due to increased snowfall. And so, as Isabel alluded to, we need to take a lot of things in context and start looking into the processes of what's driving these changes, and be careful about what we're saying about mass change and accelerations when we're looking at shorter time series, particularly with Antarctica, which has so much variability over the short term and long term. But again, West Antarctica is still doing its thing. That story that
1 minute
dominated
left.
the mass balance story, still doing its thing. Concluding, the two missions make a great combination. And so, yeah, it's like milk and cookies, better together. This technique is a novel observational constraint on SMB and dynamics and firn air change. There's been a lot of variability in Antarctic surface mass balance over the past 6 years. Firn models still need improvement. It's been the story for converting volume to mass for decades, but they're getting a lot better. And the big thing is we need to keep these observations moving into the future. So Grace C, super excited for that. And we need to get something along the line for altimetry. But ISAT2 lifetime is still the mid-2030s. So we're going to have a lot of observations and overlap with continuity. And thanks. I'll take questions when we take a break.
Very good stuff, Tyler. Thank you. All right. We'll hop into the next theme this morning, oceanography. We'll start with Andrew Delman from the Joint Institute of Regional Earth System Science and Engineering at UCLA. Andrew's going to talk about inferring ocean heat uptake from satellite durimetry and altimetry.
Thank you, Felix. What is Earth's energy imbalance? It's what's motivated our study here. It's the difference between the amount of energy going in the top of the atmosphere versus what's going out. It's been estimated to be order of 1 watts per meter squared from missions like Ceres using radiometers, but there's a lot of uncertainty in that. So another way of trying to understand Earth's energy imbalances to do an inventory of what heat is changing in the various Earth systems. And about 90% of the Earth's energy imbalance has been estimated to go into the oceans. And that's why we're trying to understand changes in ocean heat content. One way we can get at that is that ocean heat content is related to steric height. What is steric height? Steric height is the part of the sea level change not associated with ocean mass change. So we can measure this very well with satellites because altimetry measures the total sea level change, and GRACE and GRACE follow-on measure the mass change. So the difference of those is the steric height. There's been some previous work by Maria Hakuba with this approach, and using the geodetic, the satellite-based steric height to estimate OHC and OHU, and you get results that are very close to the series results from top of atmosphere measurements. But there's some details that need to be tended to here, because in order to get from steric height to OHC, you need estimates of the ocean state. Satellites don't give you the profile of density in the ocean. So we need to estimate these from reanalyses or models of hydrographic data products. And we need to understand better what's causing the many differences in the various products that estimate the ocean state. So key concept here is the ocean's thermal expansion efficiency, where you can describe the change in steric height as the vertical integral of this thermal expansion efficiency alpha, and the change in the temperature, which is proportional to the ocean heat content. So to get from the steric height, which satellites provide, we want to get to the change in the temperature, but we need to know this alpha, and alpha varies with temperature and salinity and pressure, and therefore it varies a lot with depth in the ocean. So what we really need is a kind of effective alpha that allows you to get directly from steric height to the vertical integral of the temperature anomaly. The problem is that if you try to compute these via linear regression from data products, you get some quite different results depending on which model or reanalysis or data product you use. So we're trying to look at different frameworks for doing this, but we've done a kind of preliminary estimate, just taking a number of different products, from a state estimate to the ORAS fiber analysis to Argo-based and Argo XBT hydrographic products. And so by doing a trend map based on that and using the different effective alpha for each location, each water column on the Earth, you get this kind of trend map. And this agrees very well with the various different products. You can see this in the extended slides. And also, if you do a global average of that, you can see that the green curve, the satellite-based reconstruction of OHC, agrees very well with most of the data products that we use, both in the high-frequency wiggles and the overall trend, which, based on previous estimates of the ocean heat uptake in the top 2,000 meters, about 0.6 watts per meter squared, plus minus 0.14. So we're well within that in the satellite reconstruction. So there's promise to this method, and frameworks for quantifying effective alpha and its uncertainty are being studied right now. Hope to submit a manuscript on this in several months. And there's also a workshop on Earth energy imbalance and the contributions to that next year in June in Pasadena. So you can look at that link if you're interested. Thank you.
Thank you, Andrew. All right, we'll keep going with the oceanography theme from Cecilia Peralta-Farias, University of Washington, Davis Strait ocean volume transport variability from 2020 through 22 using in situ and satellite ocean bottom pressure observations. Take it away, Cecilia.
Thank you, Felix. Good morning and good afternoon, everyone. Can you see my screen and hear me?
Yes, see you, we can hear you, and your slides are up.
Excellent, thank you. So before I dig into Davis Strait ocean volume transport variability, I wanted to briefly update you and remind you about a series of good news, followed by bad news, followed by good news, and very, very good news. So let me start with the first good news, which is a reminder that as part of the GRACE science team, my team and I in 2020 designed and built a custom deep sea Arctic bottom pressure recorder And in 2022, we deployed this at the North Pole. In 2023, we were able to recover the first year of gap-free hourly ocean bottom pressure data, and this record is available at PODAC. The main presentation in the agenda has the link directly to this record. And if you have any questions, there's a documentation there. If there's any questions about it, please send me an email. The bad news is that this instrument was built to last for 5 years. And unfortunately, to my biggest disappointment and frustration, in 2024 and 2025 attempts to recover the second year and third year of data, we were unable to communicate with the pressure sensor. So now we presume it's dead. We learned a great deal about acoustic communications under the big ship that we were operating from and that we will continue to be operating with. And we are happy to say that we, even though the acoustic communication were not the issues for this instrument, we will be able to build a new long-term BPR, or hopefully long-term this time, and we deploy it at the North Pole in the summer of 2027. Another piece of equipment that we have new in our hands now is a Sonardyne Fetch ASA, and it's a long-term, for 10 years of continuous records, bottom pressure recorder that will self-correct for instrumental drift. And this instrument is going to be deployed in summer of 2026 in the Nordic seas. Here's some map over here. It's 66 degrees north and 2 degrees east. And this is going to overlap with the 2 pairs of satellites of the constellation Magic. And but we are here now to continue with other good news. And we are going to focus here on this area of Baffin Bay between Greenland and Baffin Island. And this is the Davis Strait over here. Another pleasantly great news is that even though this is a very challenging region for GRACE, or has been very challenging for GRACE solutions to detect ocean mass changes, we have used now the monthly JPL, the most recent solutions of the MASCONs, and the CSR MASCONs, they give the exact same, almost identical results here. And we have 3 records here, one in Western Davis Strait, one in Eastern Davis Strait, and we have one in the deeper Baffin Bay up here. And all these records are very highly correlated. Well, the one in the Baffin Bay is very highly correlated with GRACE. As you can tell, the correlation coefficient is 0.71. So this was a very, very nice surprise here. The other good surprise is that, of course, we have a record of high frequency of these BPRs. So this can also help us look at the tides very carefully. This is the first record of deep tides in situ measure in this region. And the other pressure recorders are not as great as the one Baffin Bay in terms of comparisons with GRACE, but they are still highly correlated, and we had not seen this before.
1 minute left.
Thank you. And now we take these 2 records from the east and the west, and we're able to capture, to compute the meridionally, horizontally average volume transport. And the 2 take-up messages that I want to show you here, highlight here, but you will see a complete story in the PDF uploaded, is number 1, that the BPRs west and east likely capture most of the total horizontally average meridional Davis Strait flow variability. The take-up message number 2 is that the records combined with GRACE follow-on and atmospheric analysis data reveal 2 forcing mechanisms driving the Davis Strait flow. The first one is that the Arctic high sea level pressure, picture here, drives anticyclonic winds along South Greenland, and the ocean response is likely a slope current that increases the bottom pressure in the area, in the strait, within a day. This is a very fast response. The other one is coming from the southward winds along the southeast Greenland, and these generate coastal trap waves with ocean responses that are in 2 timescales. One very fast between 6 and 10 days, which is a barotropic response, and the other is a response that we see in 2 months later, and that's associated with the baroclinic response. And thank you very much. This is work in progress. We are preparing a manuscript for this, and the data for the Davis Strait is going to be archived within the next couple of months. Thank you.
Thank you, Cecilia. Those are some really interesting, nice results. Shows a bunch of questions. All right, one more talk in the oceanography block. this morning, given by Rui Pont from AR and the Janus Research Group, improving ocean bottom pressure fields through the use of space gravity data in state estimation.
Hello, everyone. This talk describes work in progress examining the value of space gravity data for constraining estimates of the ocean circulation. And my co-authors on this work are Nish Silva and Monan Zhao at AER, and O Wang and Ichiro Fukumori at JPL. So ocean bottom pressure is a key variable for monitoring and understanding ocean variability, but a simulation of bottom pressure data from GRACE into ocean models has rarely been attempted. One exception are the ocean state estimates produced by ECHO. The latest optimized ECHO solution simulates the whole GRACE record along with many other data sets. In addition to ocean local bottom pressure anomalies, ECHO also uses GRACE-based estimates of global ocean mean mass to constrain the net freshwater flux into the oceans and the associated changes in barostatic sea level. So our quest here is to examine how the gravity data affects the ECHO optimized solutions. Our first question is whether the optimization leads to relevant changes in bottom pressure fields. And we can answer this question by looking at the differences between the optimized ECHO solution and its control counterpart. The control run is done without any data constraints. The standard deviations of these differences are shown on the bottom in centimeters. And for context, we show at the top the standard deviation of bottom pressure fields in the ECHO solution. From these plots, we can see that the optimization leads to relatively large adjustments in bottom pressure fields, with magnitudes of adjustments comparable to the variability. So another important question is whether changes produced by the optimization lead to a closer fit to the gravity data. We examined this by calculating the standard deviations of the difference between the ECHO optimized solution and GRACE, shown on the top left, in comparison with the difference between the control run and GRACE, shown on the top right. The difference of these two panels is shown on the bottom left. The mostly negative values denote regions where the differences to the data are smaller for the optimized solution than for the control run. So thus, as expected in a working optimization, the optimized solution is indeed a better fit to the gravity data over most regions. All we've seen so far does not isolate direct effects of constraining to gravity data. The adjustments to bottom pressure could in fact come from any of the other data constraints used, like satellite altimetry and in situ hydrography. To shed light on this issue, we plot the RMS of bottom pressure adjustments as function of time, which is shown in green, and highlight with shading the periods where gravity data is available for a simulation. What the green curve shows is consistently higher bottom pressure adjustments over the grace period. And moreover, within the grace period, one can see typically smaller adjustments over the short period data gaps. So this points to the direct effects of gravity data constraints on inducing changes in the estimated bottom pressure fields. So finally, the other question we address is whether using ocean mean mass estimates from gravity data has an impact on the ECHO estimates. The time series representing the ocean mean mass in the control run, which is shown in green, shows a huge drop in barostatic sea level of around 30 centimeters over the period examined. This is due to well-known imbalances in freshwater flux fields from the atmospheric reanalysis used as forcing for the ocean. Constraining to GRACE global means can bring the forcing surface freshwater fluxes, particularly precipitation, into a more realistic balance. And the result of the optimization is a barostatic sea level curve that tracks very well the GRACE-derived fields. In summary, and wrapping up, our findings indicate that GRACE data contain information complementary to that available in other ocean datasets, confirming the value of GRACE data for ocean circulation studies. Thank you.
Thank you, Rui. All right, that wraps up the oceanography theme, and we're going to move to our third theme this morning, solid earth science. First up, we have Mike Chin from JPL GRACE data as non-tidal deformation and reference frame determination, effect on position time series forecast.
Hello, everybody. I'm looking for my, let's see. I cannot find the, let me try the desktop, see if this works. Huh. You see my slide?
Yeah.
Okay.
And we can hear you. You're good to go.
Okay, sorry about that. Okay, so the authors here are involved in creating a terrestrial reference frame dataset at JPL. It's called JTRF, and our interest is to simulate or ingest this GRACE data into estimation of reference frame. And this is presentation is just our initial feasibility test. So most of you here probably know that reference frame consists of XYZ coordinate of the selected sites on the surface of Earth. We need to sort of update the position of these things because of the movement. We moved across movement, plate tectonics, GIA, and so forth. And also the mass center of Earth have apparent motion because we moved. So it's about 5 millimeters seasonal change on these the center of Earth. So these things has to be tracked. However, the reference frame campaign, the estimation campaign takes place every couple of years. Used to be every 5 years or so, and now it's more frequent. But in typical applications, the positions has to be forecasted using the velocity, the linear velocity. And what gets into the way is this non-tidal deformation, NTD here, due to the loading of the atmosphere, ocean, groundwater, and then so forth. And so that's where GRACE come in. We try to estimate this non-tidal deformation and try to use that information and trying to in the purpose of making the velocity estimate better as well as the position. So so this is the experiment. If you can see yellow dots, these are the GNSS position measurements, the position data that we use to in our estimation. We just like fit a line. The dashed line is like a line, and then try to use the line that fit on the left-hand side to estimate the position on the right-hand side. So and then the variation, this annual variation, annual variation, is the non-tidal deformation. And the traditional way to deal with this is to fit a partial Fourier series, annual and semi-annual. That's represented by green line. That's a traditional method. And so the new methods, it's already established, but the blue line is to use the output from geophysical model to actually find the external data to deal with this variation. And the red line here is the GRACE data that we prepared. We have a poster, I think it belonged to the first day by Claudio Abondanza in our team to detail how this data is prepared. So the last, let's see, sorry.
1 minute left.
Yes, I'm going to the last slide here. So what happened is that, if you average over 520 or so sites that we use, there wasn't that much change. That's not unusual. But there are some bad cases that the short data to sort of do a forecast. And if you see that in the non-tidal deformation case, that there's no NTD ingested, and there are bad forecast cases on average. And when there's bad cases, grace data seem to, the more positive data, more reduction in millimeter, so reduction in error. Grace seem to do well progressively, and that's the case for others, and grace seem to excel on these things. We're still trying to investigate what exactly what's happening. There are site-by-site variation on this. But what's good news is that actually there's no degradation in forecast due to additional grace there. We didn't see a crazy forecast due to that ingestion. So that's really gives us like a really motivation to move forward with this thing. This gives us a really like a nice practical benefits that our state vector for Kalman filter that we use reduced by 1/3. So we have state vectors of 15,000 variables and with no approximation for covariance matrix or anything. So this is like a huge computational savings. So this will have a practical benefit, these. But right now we try to figure out what causes these benefits and try to move forward with this. What we need to do is to model the spatial correlation amongst the sites and when we ingest the grace data. That's where we are right now. Thank you for your
Mike.
attention.
Thank you. We'll follow up with questions in the chat. Next up, in the solid earth science block, we have Shinchan Han, now at Ohio State University. Gravity change by earthquake cycle processes expected from the MAGIC constellation.
All right. How can I share my screen? What is this, Jim? Sorry. No. I think my computer setup doesn't allow the sharing through the Zoom.
Shinchan, we can also jump ahead and you can send us the presentation. We can share from our end if that's easier.
Okay, can you share the presentation I uploaded to the website?
Yeah, give me a sec and I'll pull it down for you.
I can do that also. Yeah, you got that, Colin?
Yeah, give me a sec, so we are looking for
Number 2, sorry.
Gotcha. I gotcha. Oh, you got it. You're faster than me.
Yeah,
okay.
Is that okay? You want to start, Shinchan?
Excuse me?
Do you want to start?
Yeah.
Yeah.
If I can. Yeah, thanks very much. So this is a little bit sidetracked effort we have been doing. So we are looking at the GRACE data for retrieving all the earthquake-related signal, the co-seismic and post-seismic gravity change from the long, more than 20 years of GRACE data record. But we like to look at what MAGIC can do regarding to the solid earth deformation signal. Next slide. Probably next one. So I prepared the 2 different versions, the long version and short version, but this is the long version. So this is the list of the all earthquake we are working on. So we have the gravitational potential model of co-seismic and post-seismic change of these 12 events. Plus we are working on 3 recent events in 2021, plus the very latest one, 2025 Kamchatka. So we will be adding these 4 great earthquake into this list. Next one, please. So we are sharing all the monthly, we call GEQ gravity potential model through that website at the bottom. So if you look at the linear trend over 20 years by taking the monthly gravity coefficient model, you see the left-hand side, and if you compare with the actual GRACE measurement, you can realize that many of the plate tectonic, the tectonic boundary signals associated with the earthquake. Not all of them, but many of them. So this particular coefficient GEQ has a monthly mean earthquake-related signal, so that you can subtract those model from the level 2 GRACE product so that you get the level 2 data free from earthquake in this gravity change. Just like you add the GAC coefficient to L2 product to get the full ocean signal, you can subtract this GQ from the L2 to get the earthquake free signal. Next one, please. Or next one. Yeah, one more. Thank you very much. Maybe one more. So we are applying this GQ model to assess the magic gravity sensitivity. So we are taking the ESA SING simulation study, SING, primarily made by the TUM Roland Pyle. So we took the GRACE C only, which is in blue, and GRACE C plus NGGM combined solution, which is in red, and comparing with the model we are producing from the GRACE analysis. And we are not looking at the time series as a point, point wise. We are looking at, we are doing some earthquake moment tensor decomposition because we know the earthquake does not change the gravity randomly. There's a specific way of changing gravity field by the earthquake. So we apply such a physical model and extract the coefficient of relevant moment tensor, which is shown in this file plot. So you can visually see the drastic change between the GRACE C and MAGIC combination by factor, sometimes 5 or so. Next one, please. Yeah, this is thrust event. Next one. Yep, thank you. And this is the smaller one, the normal fault. The first one, isotropic component, there's a huge change in the first component.
1 minute left.
Yep. And you can see factor 6 improvement by adding NGGM pair to the solution. Next one, please. And this is the strike slip, pretty small. And if you look at the last plot, the right, that one, you compare, the MAGIC and GRACE C, you are talking about order of magnitude improvement. And if you, I have the full slide in the original, the PDF file in the website. If you compare GRACE C here, simulation, and actual GRACE, you can see they are pretty much, same in terms of scatter, which means GRACE, this simulation is pretty realistic. Next one, please.
How about like an NGGM only?
Yeah, NGGM only is not shown here, just to compare blue and red, GRACE and combined one. Next one, please. Oh yeah, this is the comparison between what actual GRACE data, left-hand side, and the simulation, right-hand side, at the same scale range. Yeah, so MAGIC is really improving certain component of earthquake deformation by more than order of magnitude. Next one, please. So last two slides is highlighting the ground track. So the top left shows 3 days of ground track, 500 kilometer polar orbit. The bottom is NGGM ground track, 400 kilometer, 70. So 3 days we have a much better coverage for this particular earthquake happened in South Sandwich Iceland. And the magnitude of perturbation is 3 times higher because NGGM is 100 kilometer lower. Next one, please. Probably I go to the same thing that we had a tsunami simulation by putting the tsunami geopotential in orbit integration. So we got a very similar conclusion, 3 times higher signal, larger signal can be measured from the NGGM compared to GRACE C because of 100 kilometer reduced altitude. The final slide, please, conclusion. So we are convinced by through this small study of looking at the SING simulation result, I'm convinced the MAGIC will see factor 2 to 20 improvement, and the threshold of the earthquake detection may be as low as magnitude 7.5. Thank you much.
Thank you, Shinchan. We'll move right along here to the next talk in solid earth science theme. Lambert Caron from JPL will talk about insights from earth body tide data on mantle and elasticity.
Thank you, Felix. So over the last 10 years, we've gotten more and more evidence from the mineral physics community, coming from both laboratory experiments and digital experiments, showing that we have deviations from pure elasticity in the mantle material that start at 1 hour and build up towards longer timescales. Now, this is important to GRACE because in the level 3 processing, we assume that we have pure elasticity in the love number employed. And the question that we ask is, what if the mantle was inelastic? Should we revise this to a time-dependent value? That would affect the resulting equivalent water height maps that are derived from the GRACE processing. And we're talking about something that could, we estimate, reach up to 10 or 20% at the most, at the highest range suggested by these mineral physics constraints. So one way we can investigate this revision is to look at the Earth body tide data. So this is what we're reporting here is the percent deviation to love numbers, degree 2 tidal love numbers for the real part and the imaginary part. And what you can see in this plot is that when you look at the MF time scale, which is 2 weeks, you are around 2 to 3% deviation from the elastic value, and then building up to the 18.6-year tide, you're reaching something like 12 or 13% deviation from the elastic love number. So it ends up building up and being significant. So we have investigated that in our team with ISSM, computing the range of anelastic deformation that can be generated using the extended Burgers model, a transient rheology model, and using Monte Carlo with Markov chains approach, we can see what range of parameters work to explain all of this data. So we report good agreement for all 3 love numbers and both the imaginary and real part. And the interesting thing is we can see what the partitioning between the steady state viscosity and the transient viscosity is. This is what you see in the colored maps at the bottom, how much of the viscosity is being solicited in these models. When we look at the parameter space, we see that most of the constraints are provided on the lower mantle properties, which is expected because this body type data is degree 2. And what we see is that essentially all the solutions extend on a spectrum with a very well-defined correlation between delta LM here, the transient relaxation amplitude, and tau h, which is the maximum relaxation time for the transient relaxation. So these parameters are both correlated, and we can identify that one end of that spectrum is low amplitude narrow relaxation band, and that's sort of the minimum anelasticity required to explain that data we were talking about. And then on the other end, you have high amplitude broad relaxation time scales that go up to 300 years, which would have impacts on GIA solutions in addition to contemporary loading. And so this is interesting because that might be a path to reconcile some of the outstanding disagreements that the community has had towards the estimation of the lower mantle viscosity. So we're excited about this, and this could be used as prior information in future modeling of both contemporary loading and GIA. So these are my take-home message. We have evidence pointing to anelastic deformation that can be seen in various types of geodetic and mineral physics data. And we see good agreement to explain that data with the extended Burgers material, and these results would have impacts on the level 3 solutions as well as the GIA models.
Thank you, Lambert. Move right along. Ashley Bellis Manley from UC Boulder will talk about 3D variations in viscosity, reconcile the strength of the lower mantle inferred from GIA and mantle convection.
Okay, thanks so much. I shared my slide. Can you see and hear me okay?
Yes.
Great. Okay, well, I'm really excited to present these results and really proud to be a part of this session. I found with the help of my co-authors that 3D variations in viscosity reconcile the strength of the lower mantle inferred from GIA and mantle convection. GIA is the solid Earth response to the last ice age, and it's observationally constrained by relative sea level change records. Those are time series that often span over 10,000 years at hundreds of sites around the globe. It's also constrained by GNSS uplift, which is a present-day snapshot of vertical land motion rates, changes in oblateness, or J2 dot, and polar motion. The motivation for this work is that studies of GIA have indicated for a long time, like since the 1970s, that the lower mantle is weak, and by weak I mean 6 times more viscous than the upper mantle. On the other hand, studies of mantle convection have indicated for almost an equally long time that the lower mantle is strong, in other words, 30 to 100 times more viscous than the upper mantle. There are really compelling collections of observations that are only fit on each side of the aisle by the viscosity contrast that the different groups argue for. And so in this work, we ask, can accounting for 3D viscosity in GIA models reconcile this discrepancy? Because traditional GIA models consider viscosity that varies in depth only. So we calculate the GIA response of 6 3D spherical viscoelastic Earth models to I6G using new software SITCOM SVE. The viscosity in case 1A is that of VM5A, so it depends on depth only, and it has a weak lower mantle. We consider VM5A and introduce moderate lateral viscosity variations by converting seismic tomographic model, S40RTS, to temperature and then viscosity. So that produces some moderate lateral viscosity variations. We also consider strong LVVs by changing a scale factor. And the only difference between the left-hand column and the right-hand column is that on the right-hand column, we introduce a strong lower mantle like the mantle convection community argues for. The results are that by increasing lower mantle viscosity, we see a reduction in the misfit to relative sea level records of 40%, but that comes at great cost to the misfit to uplift rates from GNSS, particularly in North America. So a factor of 2 increase is not worth a 40% reduction. That one's not viable. And this is primarily why GIA studies have indicated that the lower mantle can't be strong. The results are similar if lateral viscosity variations are moderate, but if the lateral viscosity variations are strong, like in case 1C and 2C, then the sensitivity of the uplift misfit to lower mantle viscosity goes away. So we get a 40% reduction in the misfit to relative sea level records for almost no change in the GNSS uplift misfit. And this is a really exciting result because what it means really is that the disagreement between the GIA community and the mantle convection community was driven by is the assumption that viscosity varied only in depth in the GIA models. And it seems like we can really make a big step toward reconciling the lower mantle viscosity by considering a model like case 2C, where we have a strong lower mantle and strong lateral viscosity variations. I don't have time to talk about it in this short version, but the strength of the lithosphere is a really important aspect of the strong lateral viscosity variations. So here's what this does to GRACE. Number one is what you're used to.
1 minute left.
Thanks. This is GRACE corrected for I6G with VM5A. Number 2 is GRACE corrected for my new preferred GIA model. And 1 minus 2 is the differences between them. The differences are small, but I will recommend that this could have important implications for reconciling the global mean sea level budget misclosure problem. And for more information on that, you can see my my talk from 2023 at the Grace Science team meeting. Yeah, so that's it for me. Here are my conclusions. And I'll finish there. Thanks so much.
Thank you, Ashley. All right, one more talk in the solid earth science theme this morning, Mingkang Chang on variations in the Earth's figure axis from SLR and Grace.
You put my post there, or you might file there, PowerPoint file.
I'm sorry, you want us to put it up?
Yeah.
Oh.
I can share.
I wasn't aware that we were supposed to share it. We can bring it up. Just take a second here. Okay, it's up. You're good to go.
Okay. Start.
It's not yet in presentation mode.
Right. Down there by that slider where the minus is, lower right corner of your screen. To there, that. Yep. Okay,
Right.
good to go. Yep.
Okay. My talk is about the
Just click continue to share real quick, right there in the middle of your screen.
meter square.
Continue to share right in the middle. There's a dialog box. Just click the orange bit. Yep. There you go. There you go. Right there. That.
No, stop.
No. Huh? Okay. Good to go.
Oh, yeah. Okay, it's good. You're good to go.
Okay. This talk is about this C2S21, which is characterized as variation Earth's figure axis. This issue is talk about John Wall, 1987. Also, we published a paper, the chain race of Tapley 2011, we published a paper. Now, this is 11 years, there's a 14, now this is already 14 years. We come back, look at this, what is the variation we are looking for, okay? Now, the fact that this figure axis Earth is axis minimal inertia for deformed Earth is described by Japanese C2S21. And the difference between the mean figure axis and the mean rotation pole can be attributed to the non-pure fluid motion in the atmosphere, ocean, and the core. Now, this is C2S21 from mean pole. This is according to the RES 2010. There I will show you what is this one. Now, this is how the linear model were applied. The correction from the Earth's time is depends on the mean pole of the mean pole. What the mean pole or the solar Earth pole tide or the ocean pole tide use mean pole. Depend on mean pole. Now, if this is okay, the C2S results from the what? Okay. There, okay. All of this from a Grace at the SLR analysis, AOD release 6 were used. The difference is now this I'm gonna compute the SLR determines C2S21 is we subtract the mean pole, but the Grace size process is just keep it without us remove the mean pole effects. Then I show you. First, we're talking about mean pole. The mean pole now currently the RES 2011 mean pole is used data from the 1900 to the 2015. They already now this is already 10 years later for that one. So they you say from this curve we different from this. This one is okay. This one is from the REF to the user feet is 1922. They okay. This different device. They okay. The reader one is mean pole XP from a feet to 2000 last year. This you say that from different much different. So the mean pole I think this very reprocess GRACE data, we should, I'm suggesting to recommend to update the mean pole tide extended to the 2025, 2024. This I show this one. Now this use this different mean pole, we show the different. You see this linear trait at the annual semi-annual variation from the SR at the GRACE. The black is C21 from GRACE. The S21, you look at this one. This is different, the trait is different. They will compute the linear trait from SR, the rate. What's God? Huh? What's wrong? What's wrong?
I think we lost your, you unshared the screen.
Yeah.
1 minute left.
Oh.
I mean, we might just put it up from our side if that's all right.
Yeah. Clear. Sure.
Okay, I'm just gonna go to that. It's not in presentation mode right now, but I hope that's okay.
Smaller, next.
Next slide or this one?
Okay. Grace of what?
I'm sorry?
Okay, maybe come to this part. This is more important thing. This compared to annual. This is trait.
Can you see the presentation? I'm sharing it.
No. Oh shit. No.
All right, so Felix, we have two shares going on at the same time. I'm going to kill yours because his is back up.
Oh yes,
Oh,
sure.
okay.
Please, yeah.
There we go.
We don't share. Oh, this is coming here. Come here. So that this one. Yeah. Okay, this is okay. The mean pole we recommend. Okay, this one is compared to this SR estimate C2S2. C2S2 is different from the black one is from this is from GRACE. This is from SR. This is S21. S21 rate is almost close. Okay.
Sorry, I'm not. Maybe it's just me, but I'm not seeing a shared screen. Is that just on my end here, or is everyone else?
That's yours.
Yeah, it's on your end. So go down, Felix, to the bottom and click on your Zoom icon with the right mouse key and click the other Zoom window.
Yeah, just keep going.
Yeah, we'll get him sorted out, but you can keep going. Oh. We just lost your screen share again.
Come in.
Got it back. Yep.
Okay, next up, next page. Maybe you can operate help me. Okay, this is mean pole. This is linear trait. Okay, when come to this, more important this one. You compare to this S21 from SR, T11E, and compared from C21. For longer, the blue one is the significant large amplitude for annual variation from SR. There you say here is we compare to the two. One is from GRACE funnel. C21 is smaller, very smaller. You can very smaller. And this C21 from this, okay, the reader one. This station line from atmosphere from EOP minus atmosphere ocean of the motion terms. Then okay, the second one is from the smaller one is from hydrologic signal. The interesting is this one is you say SR determines annual signal is very large to this one. They will come back to look at if you look at before the John already analyze about the code from the atmosphere the code. They will use S2 if we subtract from the code effect, the torque effects, they will compare to the EOP, both EOP. But still, the grace signal is smaller.
Ming-Kang,
Okay.
if you could come to the last slide, please.
This last slide,
Okay.
last slide. Okay, the S21 is S21 most comparable to still the grace is smaller. This annual signal. So I think this is I'm not sure for SR they capture the ocean or the motion torque of the C21. Of course, the S21 effect is smaller, but the grace didn't capture this signal. So I'm not sure what I still do not understand. This but now the SR they capture this signal, the torque signal. So we will explain or use the grace data maybe consider to use this SR determine C21, S21 for either replace grace port. This is my port. Okay.
Thank you.
Thank you.
All right. Let's move along on the home stretch here. Last theme for the day, interdisciplinary. We're a little bit behind time, but hopefully you can stick with us to the end of this last block. 4 more talks, all very exciting. First one by Yolanta Nastula on the evaluation of polar motion excitation using CS21 coefficients from hybrid SL-Doris solutions and hydrological models.
So, good morning. I will present our work about hydrological excitation of polar motion from hybrid SLR plus Doris solution, and it is teamwork. You see here my co-authors. Next slide, please. So, in this study, we focus on the impact of the hydrosphere on polar motion, which is described by hydrological angular momentum. Hydrological angular momentum we can obtain from hydrological models, from climate models, and from gravity data. And of course, GRACE and GRACE follow-on satellites provides very well gravity data, but for the lowest degree terms, satellite laser ranging seems to be more reliable. In our previous studies, we showed that hybrid solutions, so I mean solutions combining SLR observation with GRACE empirical orthogonal patterns reproduce hydrological signal in geodetic polar motion very well. In this study, we use updated hybrid solutions, so combining SLR and Doris satellites. Next slide, please. So we use 2 methods of computing gravimetric excitation of polar motion, either from variation of C21, S21 coefficient or from terrestrial water storage anomalies. And results are not identical in this case. And the reason is not difference between the methods, but in the difference in the input data. For example, whether terrestrial water storage refers only to land areas or refers to both land areas and ocean areas with ocean model being removed. Next slide, please. So data and methods, data are really important here. So we have 4 sets of excitation computed from 4 different sets of GRACE data, from coefficients computed from both spherical harmonics on mask-on solutions or from terrestrial water storage with ocean being masked out on not masked. Also, we have hybrid solutions, so about more than 50 individual solutions and 2 mean ensemble, and also hydrological models. Hydrological signal in polar motion is determined as a difference between geodetic excitation and sum of atmospheric angular momentum and oceanic angular momentum. It is called GEO or geodetic residuals. And we focus on non-seasonal variations obtained by removing trends and seasonal components. These variations are split in short term and long term. And analysis compares correlation coefficient and percents of variance explained. Next slide, please. So it is example of our results. So these diagrams show diagrams percent of variance explained versus
1 minute
correlation
left.
coefficient. On the top for short period variation and on the in the bottom for long period variation. So we may see that the best agreements are obtained for mean ensemble based on SLR hybrid solutions. Next slide, please. So it is example of correlation analysis for a case for K1, non-seasonal shorter variation, on the left time variable correlation, on the right corresponding global correlation coefficient. So we start from results based on two mean models, then we see results for individual solution, starting from small number of harmonics and EOF. Then we came through 4 hydrological models and 5 Grace models. And we see the best results are obtained from SLR only hybrid solution, mean model, then for SLR plus Doris hybrid model. Also, we see that increasing of number of harmonics and empirical orthogonal function results in better correlation, but there are also periods of weaker correlation common for hybrid solution, hydrological based results, and also for Grace. Next slide, please. So there are our conclusion. So main conclusion is that hybrid solutions are very useful for studying hydrological excitation of polar motion, especially in the non-seasonal band. Best results are obtained for mean models based only on SLR hybrid solution, better than for SLR plus Doris solution. Results depend on the number of harmonics and empirical orthogonal functions, and future work should focus on periods of weaker agreement. So thank you for your attention.
Thank you, Yolanta. Okay, we have 2 talks coming up looking into Earth rotation variations and anomalies. First one is going to be given by Leonid Slotov.
Hello, can you hear me? Do you see my screen?
Yes.
Greetings from Samarkand. That's my answer to Jean-Michel Lemoine yesterday's request. I will speak about usage of Grace data for explaining EOP anomalies. By anomalies of recent epoch, I call the disappearance of free coordination, the maximum of Earth rotation velocity, and disappearance of the Chandler wobble. So what we can get from Grace is C20, C21, CS21, and what is called by Yolanta hydrological angular momentum, and probably tides, which are usually removed. I will not speak much about free coordination signal. We will skip this subject. I will talk about LOD. So we know that in recent epoch, we have a minimum of length of day, and it is a maximum acceleration over 80, almost 90 years in 1930s. We know that from Grace we can obtain J2 estimates, and their effect in LOD is below 0.1 millisecond. And that is what Agnew used in his paper, saying that climate change decelerate the Earth, and real picture is acceleration more than by 1.7 milliseconds this year. This plot covers 3 years of LOD variations, and we were expected the minimum deeper than in 2024, but this year minimum was on the 5th of August, not so deep. And there were publications in press, in popular media, Time and Date, and even Forbes, the New York Times, and Elle. They were interested in what's going on with this rotation. And this minima, they are usually related to there are several effects: decadal acceleration, annual acceleration, and tidal acceleration, fortnightly tides with 14 days period related to the moon crossing the equator. We know that C21, S21 coefficients are in agreement with polar motion drift. X component, Y component, there were many publications. But besides the trend in polar motion, we have disappearance of a Chandler wobble this year. In 2017, it almost disappeared. In 2020, it appeared again, and it seems that the phase of the Chandler wobble shifted by 180 degrees. We were thinking what could be responsible for that, and found out that very interesting thing. I should be thankful to Sidorenkov, my teacher, my professor, that perigee is moving eastward and nodes are moving westward, and they meet in the sky every 6 years.
1 minute left.
By these triangles, we show where in the sky and when perigee meets the node. This epoch, 2024, 2006, perigee and nodes, they meet exactly at equator in spring equinox. There was eclipse on the 21st of September this year, and now the moon is in perigee in full moon. Last time it happened 90 years ago, and next time it will happen in 2110. We think that disappearance of Chandler wobble occurring exactly, at least we have two prominent events of this kind. It occurred in 1930s when LOD was in minimum, and it occurred now when LOD is in minimum again. So, conclusions. Grace and Grace follow-on mass term explains small changes in LOD and almost all polar drift. So climate change can be the reason for some Earth rotation deceleration and change of polar motion drift, but disappearance of LOD and Chandler wobble cannot be explained by the mass component of excitation. But if we found out, maybe it's a hypothesis, that tidal mass transport has relation to these anomalies, then we can extract better tidal models from Grace and probably understand what could be the reason according to our hypothesis. Thank you.
Thank you, Leonid. Next up, we have Don Chambers, University of South Florida. He'll talk about the primary oceanic sources of seasonal to interannual Earth rotation.
Thank you, Felix. You should be able to see my screen now.
Yes. Can see you, can hear you. Good to go.
All right, so I'm looking at the oceanic sources of Earth angular momentum, polar motion, mainly focused on where in the ocean is driving the majority of the signal. The data set that I'm using is a Grace MassCon data set, but it is one that we have just recently released that attempts to break the standard MassCons into a geodetic signal from the mass redistribution from land to ocean, the GRD and barostatic sea level, and one that really represents as best we can the dynamic ocean variations. So, the takeaway from this is that while the GRD and barostatic has some trends in the polar motion, earth angular momentum, excitation functions, the dominant interannual and seasonal type of variations are coming from the ocean. So I'm going to be focusing on that now. Again, I'm using excitation functions as has been discussed previously. So I'm doing several experiments here. When I talk about full dynamic ocean, that's just the integration of all ocean mass cons. I'm also looking at a redistribution term. This is looking at a large-scale mass redistribution between the Pacific and the Indo-Atlantic Oceans, which I've documented previously, and others such as Rui have documented in models, and it's a fairly well-known phenomena. And then I'm removing that signal from the Pacific and Indo-Atlantic basins and creating what I call Pacific internal, Atlantic internal, and Indian internal variations. And so this is what's left over from that large-scale redistribution. And then I throw the Arctic in there, but I can tell you it doesn't have much of an effect. So here are the basic takeaways. In the upper left is the redistribution variations. You can see they're quite large on interannual and annual timescales. That primarily affects the Chi-2 polar motion term. For the Chi-1, it's mainly driven by Pacific internal with a lesser contribution from other basins. And Chi-2 Pacific Ocean internal also affects it on an interannual basis. And so if we do a low-pass filtering to really focus on the interannual, you can see that for Chi-1, the Pacific is about 62% of the variance. The Atlantic contributes a little bit, 33% of the variance. And then in the Chi-2, it's basically a combination of the Pacific internal and this large-scale mass redistribution. They contribute more or less evenly to it. I will say that, from some preliminary analysis, most of the variability in periods between 1 and 2 years appears to be coming mainly from the Pacific internal variations. And so the goals now are to quantify where exactly in the Pacific is causing this. Is it one area, or is it just variability all over the Pacific that's driving much of this?
1 minute left.
I'm done.
Excellent. Thank you, Don. All right. We have one talk left, last but not least, certainly, Donald Argus on the interhemispheric fluctuations in Earth's water, snow, and ice from space geodesy.
Got it.
Are you going to share from your end, Donald?
Yes.
Okay.
Laser ranging to the spherical dense satellite LAGEOS provides an estimate of the displacement of Earth's mass center, CM. We can compare that estimate to the value gray sites assume movement of total mass of the atmosphere.
Donald, do you want to hit that button in the middle, continue to share?
Yeah, what happened?
There you go.
Yep, you got it.
So we can compare this estimate to the value Grace scientists assume movement of total atmosphere, oceans, and continental water to be. The big question is, how do we define solid Earth on the basis of laser sites on Earth's surface? For decades, geologists took the geodetic network center to be the solid Earth's mass center. CN is the mean displacement of geodetic sites. We maintain this estimate to be bad because most SLR sites are in Europe and North America, and in the winter they subside in elastic response to snow accumulation. So plotted is a phasor diagram, CN relative to CM. The distance from the origin is the peak-to-peak seasonal oscillation. The angle is the time CF is maximum. And CN right here suggests there to be twice as much inter-hemispheric mass movement as assumed by Grace right here. We next plot the displacement of Earth's figure center, CF, as determined by Rebishong 2024 using 1,000 polygons entirely covering Earth's surface. This comes close to TN13 plus GA plus GAB, the value we assume in Grace. That may be good, except that geodetic sites on islands may not reflect displacement of the ocean floor, which comprise 2/3 of the Earth. In this study, we estimate the displacement of ECF as follows. We postulate that fluctuations of atmosphere, oceans, and continental water are the sole phenomenon deforming Earth's surface. We remove from the observed geodetic site displacement solid Earth's elastic response to CF created by these three mass phenomena. We then calculate the mean displacement as before. ECF is by definition equal to CF, and we find ECF from the same SLR data set to be nearly equal to that from Grace. The three key points are, if we were to correct for elastic response relative to CM, we would attain an estimate of ECM relative to CM with which to check the CM estimated from satellite tracking. From SLR, we find these estimates to be 3, 2, and 1 millimeter. That's the level of accuracy of the estimate of CM from SLR. We conclude models of continental water, atmosphere, and oceans are to a high degree consistent with geodetic observations of Earth's mass center. Key point 2 at JPL, Haynes et al. Strengthened the GPS SLR using signals to Grace adjacent low Earth orbiters, and that enhances the determination of this displacement of CM. And then we find from our check, ECM is close to CM with the differences being 2 millimeters per year in X, Y, and Z. Therefore, we can bring confidence to the Grace breakdown of total water in atmosphere, oceans, and continental water. GAA is the atmosphere, GAB is the ocean, and GSM is continental water and barostatic ocean. And so we're finding winter snow accumulation in North America and Eurasia in March. It's about 3,500 cubic kilometers. That causes Earth's mass center to move back and forth along the spin axis, 3.2 millimeters. And the atmosphere mass is maximum in late December, 3 months earlier than snow is maximum. Snow and soil moisture is maximum in March. Thank you.
Thank you, Donald. All right. we got through all our presentations, had a few technical hiccups along the way, so we've kind of blown through our allocated time this morning, but I do want to give the opportunity to ask questions. Hopefully you can stick with us for about 10 more minutes or so. You can either raise your hand or we can just revisit some questions in the chat. There's been some pretty good activity this morning in the chat already. I don't see a raised hand just yet.
I have a question.
Min-Kang, did you have a question?
Yes, I have a comment about the CM direction determination. Only I said ESSA determines CM is for dynamic, not geometric. Dynamic approach is based on the ground track, coverage of ground track, almost most coverage almost whole Earth from multi-satellite. I think that I have the paper, the 2003 or 2023, the new paper. Okay, the updated estimate geotheta. So please look at this, my paper. They will understand the difference. All the comments.
Thank you. You can put that reference in the chat maybe so people can follow up. Are there any other questions? I think most of the questions in the chat were answered this morning. I had maybe a question, a quick question to the cryosphere folks. Just in general, the last few years we had often co-analysis of the ocean's influence on the ice sheet changes through programs like OMG. I'm not sure if OMG is still going on, Oceans Melting Greenland, or if there's a complementary program around Antarctica. But what is the role, or recent role anyways, of the ocean for the interannual variability or recent changes? Is there a consensus on the ocean's role on that front? So this is to Tyler or Ingo. I think Isabella had to drop off.
Yeah, so the ocean component is definitely driving what's happening in West Antarctica, the ongoing mass loss that we've had for the past 2 decades. Decoupling atmospheric and oceanic forcing is complicated, but what we're seeing in terms of the more recent mass change is snowfall driven, but that could be due to, which is atmospheric forcing, but it, whether it's one of the teleconnections that has oceanic in its background, that's a more deeper question.
Oh, OMG has ended, right? Is that correct, or is that still going on?
It ended, yeah. There's a new airborne campaign that's in the works called Snow for Flow out of Goddard.
Okay.
Yeah, OMG ended.
Gotcha. All right, David, you have your hand up. Go ahead.
Yeah, I had a question, maybe for Evan. It was the first talk going all the way back to the beginning, but it's really on LRI and KBR differences. So I thought you had a conclusion that said that the LRI was revealing, signatures that the KBR couldn't. And I guess, kind of a specific, I didn't really see it. I may have missed a comparison between LRI and KBR that would maybe warrant that conclusion, and maybe you had it, but I was wondering if you could just kind of talk about that. This is just something that was always coming up, is quantifying what the LRI is capable of that KBR maybe is not. And I want to make sure I understood what point you were getting to.
Yeah, let me share my slides again, because so the comparison between ICESat, the synthetic LGD, from ICESat with LRI and KBR LGD, you can really see from the 100 to 150 CPR, which is significantly beyond what the level 2 solutions allow us to see because of that temporal aliasing. You can really clearly see that the KBR here, which is -2 to 2 nanometers per second here, is completely saturated by noise. While for the LRI, you can really clearly see this real mass change signal in Western Antarctica, Totten Glacier, even Antarctic Peninsula, that's also really reflected in this ICESat. So
Evan, just like on top of that, a clarification, right? KBR, if you check the instrumentation noise, it really spikes as you go above 90 CPR. Please go back to that. Yeah. So if you could actually filter that not between 100 and 150, but between 100 and 120, then you will see probably some lingering signal. If you go and see for your previous, can you go to Antarctica plot? If you check your Antarctica plot, you had to change the legend and put up to 5 or 2 nanometers, because everything there is noise. If you actually play a little bit with the band that you filter, you may be able to match the signals, right?
So I've also performed more like specific filtering analysis for the KBR, breaking it down in that 60 to 100 CPR band. And my conclusion was that beyond 85 CPR, the KBR is not really resolving anything. And certainly in the 100 to 150 CPR, I mean, the PSD is very clear that the signals are, larger than the actual gravity. So it's not decreasing like in the PSD like we'd expect for any gravity signal. So my conclusion with that is that KBR is really not sensitive to mass changes beyond around 85 CPR.
Which is pretty much in agreement with what we've seen. We've published that a few years ago at JPL. It goes up to 95 CPR. And that's why I asked whether in the chat, whether there's like some annual signals in it, because they can actually, they have high magnitude. So yes, LRI can pick them up in these very high, nice spatial resolutions compared to KBR. And that's a great finding. But when we actually go and take out signals and kind of look at sub-monthly or monthly, then the two instruments are pretty competitive. All right. It has to do with how we treat our signal. But that's a great work. Excellent work.
Thank you.
Okay. I want to be respectful of people's time, but I have a quick request. So one, I invite you to turn on your camera, and usually when we meet in person, we do a group picture. I forgot yesterday to do a screenshot when people are on, so I'm going to do that. While I'm doing that, please feel free to also continue to ask questions. It's a quarter to the hour. I'm happy to stay on until the top of the hour, but I know people might have made plans or different plans. I'm going to take screenshots. Feel free to ask questions. I have to flip through some multiple panes here.
Felix, I'm back again on the verbal version. That hand up version operated once this morning. It does not operate now. I'm not sure what's happening there, but in any event, this was more a question that I had for Isabella, but it may be that one of the other cross-set presentations could go into it. There were some fairly significant differences between the surface mass balance and the GRACE results, and some of the trend relates that Isabella shown. Is that understood what's happening in terms of it? Places they agree very well, other places there were quite large divergence, and I'm not sure understand what that would be about. Did anyone else pick up on that or have any opinion on it?
So Isabella had to drop off, but Tyler, go ahead.
That'd be the dynamic signal. So changes in ice flux largely due to oceanic force is how they diverge. So the surface balance is how we sort of try to model the atmospheric components, so precipitation and melt. But GRACE is measuring the whole integrated signal, and so that includes changes in ice flux.
So this is really then a difference in the signal. The atmosphere is not included in that. That's a big, some of those were just horizontal slopes, others were fairly substantial trends going into it. That's a big difference. I wasn't aware that was good. Thank you, appreciate it.
Okay, are there any more questions or comments? I had a sort of one remark, a question to the ocean folks, Rui and Cecilia, Andrew for that matter too. So when you take our data products, we have not removed, at least the standard data products, the GRD, the fingerprint, gravitational rotational deformation. Would that make a difference to your analysis? Obviously, when you assimilate it into the ocean model, that's a non-dynamic signal. And so just on that note, we have pushed out actually a complementary GRD fingerprint data set to the JPL MassCons, and I know it also exists on the European side. Gravis has that. We haven't advertised it much, so that might be interesting for you to actually subtract from the MassCons to extract the dynamic ocean bottom pressure part. So it's still in a bit of a test drive. Some people have had access to it, or everyone has access to it, but we just haven't advertised it. But would that make a difference to your assimilation, Rui?
Yes, it would. And we've been waiting for some of these things to happen. And I think Don also has put out another data set that takes care of the GRD. And of course, when we do the simulation, part of that might go into data noise because it's kind of missing from the ocean model. But yeah, certainly we look forward to using that. And it's good to know that you have a data set for the JPL MassCons.
Yeah, well, I'll point you to it and be always interested to get feedback. Yeah, Cecilia?
Do you expect this to be removed from the release 7 solutions, or will we have to also remove it independently?
We haven't discussed that. The default plan is to not remove it because it's it's ocean bottom pressure, which that you would measure it. The question is it dynamic or not?
Right.
Obviously, right now we're also not removing earthquakes, and they're in ocean bottom pressure, and they may not actually be real ocean bottom pressure, but they're so. Yeah. Happy to get feedback from the community. What are the most useful data products and that have the most utility, the most flexibility for analysis?
Yeah, in my case, because I'm looking at time series that are shorter, perhaps there's no much difference. I'm guessing only, but I can look at what difference it will make if.
Yeah, the only thing I was thinking, you are looking very close to mass sources like Greenland, so
Yep.
the relative impact of the fingerprint right there is large, I would expect, or has the potential to be large anyways.
Yeah, it would probably make a bigger difference in the ones that are closer to the coast, which right at the Davis Strait, probably that will be.
Right.
Yeah, I would take a look into that too. Thank you.
Hey, just Cecilia, just to kind of follow up on that, as Rui said, we have released this dynamic ocean MassCon solution. And it's publicly available. It's online now, so you can download it and take a look at it. It'd be useful for other eyes on it.
Perfect. Yeah, I will take a look at this. Thanks, Don.
Yeah, you can reach out to me or Jenny or Nadej P at CSR, and we can point you in the right direction.
Great. Thank you.
Okay, very good. Are there any questions for the solid earth or interdisciplinary themes? There was a little bit of discussion related to earthquakes. Are there any remaining comments or questions on that front? Don't hear any. All right. Well, we're close to the top of the hour, so I think I'm just gonna close us out here from the meeting. I did want to just have a few final remarks at the end here. So first of all, thank you to all presenters and participants for being here 3 days. Every day we had well over 100 participants. That's really great turnout. Really happy to see a lot of younger students taking up the baton. Lots of great work going on at new places too. So really happy to see that work. Happy to see you here and looking forward to see you at other meetings. You can always email us feedback and questions here. This is a dash or an underscore. Both addresses should work. I know I've used both in the emails, somewhat confusingly maybe. Just as a reminder that was an emphasis in my presentation, and we'll be going through the NASA Senior Review next year, meaning we will need to make the case that Grace Follow-On continues to deliver excellent value for science and applications. We will need to demonstrate that to NASA so that we can have an extended mission towards overlap with GRACE continuity. I've seen a lot of great material here in this meeting. I will certainly would like to use some of that. If it's not published yet, I will reach out to you and ask for your permission to use any figures. What I've seen with this lightning format, on the one hand, you cannot go into any detail, but it does force you to condense things in a digestible format for a short period of time. And that's actually a really great way to also communicate to our managers and sponsors at NASA headquarters. JT and I and others, we deliver sort of monthly or bi-monthly updates towards our program managers, program scientists, highlighting the findings. So if you can communicate your findings, think of like you're communicating to your parents or aunt or something, right? At that level, that's really the right level that we're looking for information to communicate things upward. That's really helpful and has a lot of value for us. And that feeds back to you then because we get to keep the mission going. So just a shout out, a thank you, and also a note to keep doing that. I think this is a great way of floating that upwards. As always, after the science team meeting is before the science team meeting. So I want to invite Frank Fleckner here to announce the next science team meeting next year. Frank?
Hi, Felix. Can you hear me? We are
Yes,
sitting
yes.
in the meeting room of GFC and Oberpfaffenhofen, also with David here. Yeah, first of all, I think I can congratulate you and your team. That was really an excellent meeting. When we discussed the format of the Great Science Team meeting 2025, I was a little bit skeptic on the format that it works, but I think most of us, or everyone, can agree that this was really a good format. Yeah, so this appetizer 4-minute presentation really, let's say, invites everyone to steep a little bit deeper into the presentations, which can be downloaded. I think most of them are available, so I will definitely look into them in the next days. But I was also a little bit disappointed that we have not an in-person meeting, because I wanted to see many of those which I have seen here now in the list of participants. First of all, Byron here, and I saw also Mike Watkins and Srinivas, all the colleagues which I have worked with since more than 25 years now on Grace Forlorn, and also pardon here on realizing Grace C. I will miss that because maybe some of you know that I have to retire here in Germany in February. So I can only invite you to come to Potsdam next year in October. I'm not sure if I will welcome you or my successor at that time. We will have to see how it evolves. I hope that your government will allow you to travel, because shutdown has happened the last 20 years, and that's the first time that we saw that you are not allowed to travel, my understanding. So I hope the situation improves till next year, that the US colleagues can be in person in Germany. And I'm looking forward to see many of you again, because I'm still planning to be in Potsdam in October, privately, or maybe still as a guest of GFC, who knows. So having said that, I wish you all, let's say, a good way in science. I think the future is really bright. We have still a good operating Grace follow-on mission in space. As Felix mentioned, the operation is secure till 29. We will see Grace C in 28, and there will be a MAGIC or NGGM mission together with Grace C called MAGIC in space. So the future for all the young people here in the audience is really magic thing. Okay, that's all I have to say.
Thank you, Frank. Thank you. Yeah, it's unfortunate we cannot be together. I really appreciate all your hard work over the last years, decades. Cannot express that here through the screen. Very much hope that we will see you next year in person at GFZ. Can only second that, and many of you. So in the meantime, we will be in touch. We will communicate the project status updates and invite you to also provide feedback, like I said. And yeah, be well. Keep doing the good work. I think, we will focus on the things we can control. And if we do that well, I think we have a good chance of continue doing this work in Grace Follow and in Grace Continuity. And I'm very pleased to see this turnout. And I wish you a good rest of your week, good rest of your day. And we'll see you again in Potsdam in October next year. Take care.